Good evening, everybody. Welcome to the Nobel Lectures of 2025. On behalf of Studium Generale, the Faculty of Science and Technology and the University, good to see that everybody turned up this evening in large numbers. In Twente, the local football club once had a saying, once we will be the champions. And indeed that happened. And in Twente University, we once will have the Nobel Prize in our university. But until then, the next best thing is other Nobel Lectures here. So you can witness this today again in 2025. There's 3 Nobel Prizes that are going to be discussed, as usual, physics, chemistry, and physiology and medicine. And we've found 3 fantastic speakers, 2 outside of the university, or almost outside of the university, and 1 from within our midst. It was a good sign that we found the speakers very quickly after the awarding in the beginning of October. And well, I'll start introducing the first speaker, Wendy Dankers, who is actually an alumna from our university, who studied BMT, biomedical technology here in Twente, and then moved to Erasmus to do her PhD. And afterwards she moved to Amsterdam for her research and is now a specialist on immunology, which is linked to the Nobel Prize of this year. Please, Wendy, tell us all about it.
I hope that the microphone is on. I think so, right? Yes. All right. Thank you very much. Good evening, everybody. It's nice to see you all here, and it's really good to be back in Enschede after quite a few years. It's also good to be back in the Vrijhof. I spent a lot of Tuesday evenings next door in the audiozaal, dancing at For Happy Feet. But today I will stay here and tell you a bit about the Nobel Lecture of the Nobel Prize for Physiology and Medicine, which was won by these 3 people, Fred Ramsdell, Mary Brunkow, and Shimon Sakaguchi. And they got their Nobel Prize for their discoveries in the field of peripheral immune tolerance. And if I want to explain why this is important, I think it's good that we're all on the same page, and we'll start with a little bit of basic immunology. So our immune system, the main task of the immune system is to fight off pathogens, bacteria, viruses, parasites. And once they enter our body, they encounter our first line of response, which is the innate immune response. This is a non-specific response. It's a very quick response. It is very broad, non-specific, but it's reasonably effective. The first cells that the pathogens encounter are the phagocytes. Phagocytes are the big eaters of the immune system, and they basically eat up those pathogens. There are multiple types of phagocytes, but for today, let's just focus on the 2 most, I don't want to say most important ones, but I will offend people. But the macrophages and dendritic cells. And these, as I said, they eat up those pathogens, and they also activate the rest of the immune response. And the first way they do this is by recruiting other immune cells that govern this innate immune response and that lead to the clearance of the pathogen. The activation of the innate immune system you've probably experienced, all of you. You've seen it. It is, for example, what happens if you get a cut in your finger and it gets red and swollen, painful. That is your innate immune response activating all the troops to fight off any potential infections and to heal that wound. That's your innate immune response. Your innate immune response is very broad and non-specific, and for a number of pathogens, this response is not going to be enough. Like, for example, viruses, like flu virus. You need a more specific, more targeted, strong attack. And this is where the adaptive immune response comes in. So this is the specific immune response, and this can be activated by all of the phagocytes, but the most important activators are the dendritic cells. So I'll just keep talking about dendritic cells, but know that also other cells can do this. Dendritic cells start the adaptive immune response by activating T cells. And broadly speaking, there are two types of T cells. T helper cells, which help It's not surprising. And cytotoxic T cells, which kill. I want to go a little bit further, deeper into this T cell activation for the moment, because it's important to understand this specificity. So dendritic cells, they don't only eat up the pathogen, they actually digest it into small pieces, small peptides, that they then present on their surface on a molecule called major histocompatibility complex, or MHC, that's easier. And they present it on their surface. It's like a serving platter for the rest of your immune system. Hey guys, look what I found. Do you want to do something with this? That's what the dendritic cells do. So they have that antigen, so we call this at this stage an antigen, which is presented by the MHC. So this whole process is called antigen presentation. They move to the lymph node where there are T cells, and those T cells, each T cell has a unique T cell receptor. These T cell receptors, they literally every cell has a unique one. Like there's 10 to the 50, between 10 to the 15 and 10 to the 20 possible T cell receptors. So it can be very unique. And your dendritic cell says, hey, look, I found this. And then your T cells will start probing. And only when the T cell receptor exactly recognizes the combination of the antigen and the receptor, that's when you get activation of your T cells. So this is very specific and very dependent on that T cell receptor. So once this activation happens, those T cells can start doing their jobs. So the cytotoxic T cells will start killing. So they will start killing infected cells, and the T helper cells will start helping. So they help all of the other things that I showed in this figure already. But one of the most important things that they do is they help the B cells. B cells are another type of immune cell. I promise this is it for the types of immune cells. B cells are the ones that can differentiate into plasma cells, and plasma cells are the ones that produce antibodies. I think we've all heard about antibodies. There's been a lot of talk about antibodies around COVID. Antibodies are actually also very antigen specific, and they can bind to your pathogen, and that's basically like a flag, like, hey, here's something that doesn't belong here, please clean this up. That's what the antibodies do. So this whole antigen-specific response, this adaptive immune response, takes about 5 to 10 days, so takes a while for it to settle, which is why if you've got a good flu infection, it will take 7 to 10 days to clear it, because you need your adaptive immune response. The nice thing about this adaptive response, though, is that it's got memory. So once the pathogen is cleared, some of the T cells and B cells will remain in your body, and the next time the same pathogen comes around, your immune system is like, I've seen you before. And then it doesn't take 5 to 10 days again, but only 1 or 2 days. So then you get very quick response and you don't get sick. And this is the basis of vaccines. We train the immune system with a little bit of the pathogen, so you already have some immunity, and you don't have to wait for this whole cascade to start. So this sounds pretty good, right? We like this. We don't want pathogens in our body. The problem is that I said at the beginning that the main function of the immune system is to fight off pathogens. But the immune system actually also has other roles. So one of the things is wound repair, like I said, with the cut in your finger. But another important thing that they do is they clean up the dead cells in your body. I don't know if you know this, but every second, 1 million cells die in your body. We don't want those to linger, because that would become a bit messy. So those need to be cleaned up. And this is one of the things that the phagocytes do. So if they see a dying cell, they will just eat it up. But phagocytes do what they do. They eat something up and they start presenting it. But then they are presenting your dying liver cell, for example. We don't want an immune response against our liver, right? So how does the immune response know to respond when it's a pathogen? and not to respond when it's something from our cells. So we don't want this whole cascade if it's our dying liver cell. We only want that if it's a pathogen. So the question is, how does the immune system know what to tolerate? And there we have the tolerance term already from the Nobel Prize. So starting in the 50s, 60s, people started to make predictions about what would cause this tolerance. And in the 80s, part of it was proven, and this is a process that we now know as central immune tolerance. And this is a process that actually happens in the development of T cells. So T cells, they form in the bone marrow, and then they go to the thymus to be properly trained, so to say. So when they arrive in that thymus, I said before how many different T cell receptors you can have. You've got a lot of different T cell receptors and T cells within that thymus. Within that thymus, then there will be a selection of the T cells that will be useful for your immune response and not detrimental to your own body. And this happens in two stages. So the first one is positive selection. I said that the T cell receptor needs to bind to that MHC molecule, but each of us here in this room probably have a different MHC molecule. So it's important that your T cells actually respond to your MHC molecule. And that's the first thing that's tested. So the cells in the thymus, they can actually create made-up antigens. So they just randomly throw together some peptides, make an antigen out of it. And if your T cell sort of responds to this, they know, okay, at least it can respond to the MHC. So what it does here is whenever a T cell actually responds to this MHC complex, it can go through to the next round, and otherwise it will be deleted. So the ones that are reactive to our own, that can bind to our own MHC, they go on to the next round, which is negative selection. And here the cells of the thymus actually present self-antigens. And the cells in the thymus are very cool. They can express antigens from every cell in your body. So they can present cells from your brain, from your gut, from your skin. So they can really select which T cells respond to those self-antigens. If a T cell shows a response to that self-antigen, it's deleted. If this went a bit too fast, you can just remember this. The goal of this whole process is that only cells that can respond to an antigen but not your own, they are the ones that can leave the thymus, go into circulation and do their jobs. The problem is that this deletion is not 100% accurate. I mean, nothing ever is it? And also, the thymus loses function throughout our life. So it's most active when we're really young, but by the time you're 60, your thymus is almost completely replaced with fatty tissue, and there's no T cell selection anymore. It can't be, yeah, I see surprised faces here. It can't be that you have no tolerance left then, right? Because otherwise everybody would die after 60. That doesn't happen. So there must be another layer of protection. And this is where the idea of peripheral tolerance comes from. So there must be another layer of protection where in the tissues themselves there must be some type of immune suppression, something that regulates that immune response. The question was, does it exist and which cells do it? Well, that it exists was shown in already in the 70s from this type of experiments where they used rats or mice, didn't matter, same result, where you remove the thymus when the baby rat was just born, and then you get a very overactive immune system in these animals, and they get a lot of autoimmunity because those T cells were not trained in the thymus. The cool thing is, if you add lymphocytes, and that's a mixture of T and B cells, if you take lymphocytes from a healthy mouse or a rat, and you put them in those mice that don't have a thymus, they will be healthy. They don't just spontaneously grow a thymus. So there must be something within this population of lymphocytes that suppresses that immune system. So yes, there is such a thing as peripheral tolerance, but which cells do it? And this is the experiment that inspired Sakaguchi and his work. And in 1982, he was finishing his PhD. And he tried to figure out exactly which cell type it was that conferred that protection. And in his work in 1982, he further zoomed in and classified, okay, it must be the T cells that are CD5 positive and CD45 RB negative. Forget about those markers. It was a specific subset of T cells, but not a completely specific subset. And also there were no good antibodies to really hone down on specifically what the properties of these cells were. So he kept working on this, and 13 years later was the work that gave him the Nobel Prize, where he was able to identify that it was the CD25 positive T helper cells are the ones that confer this immunosuppression in these mice. Okay, so this was a major breakthrough. We now know which cells do it. The problem is that CD25 can also be expressed when T cells are activated. So not only when they are suppressive, but also when they're activated. And there wasn't a really specific marker that identified those suppressive T cells, which first of all made people skeptic about, do they really exist? Like, is this real? And also it's difficult to study something if you don't know what it looks like. So the question remained, what gene identifies these suppressive T cells and drives their function? And this, I think, is actually a brilliant story. It started in the 1940s and 50s in the Oak Ridge National Laboratory with Leanne and William Russell. And they were mammalian geneticists, and they kept a whole mouse facility with a lot of mouse lines. Some of them were generated in the Manhattan Project to look at the effect of radiation on mammalian genetics. And from these experiments, there was this one mouse line, which they named the scurvy mouse, which had widespread autoimmunity, wasting disease. Those animals were very, very sick, but only the males, not the females. The females were completely fine. So this suggested that there must have been a mutation on the X chromosome. Who knows what it is? What would happen in today's science is, oh, we don't know what it is, let's kill the mouse. These people kept those mice breeding and alive for over 40 years, just because they thought it's probably important. We don't know what it is, but it's probably important. And it was. It was. So that was good foresight from these people. And this is where Fred Ramsdell and Mary Brunkow come in. Because they got curious about this scurvy mouse, and they thought, so Fred is an immunologist and Mary is a geneticist, and they thought, let's try to figure out if we can find what mutation this is. Sounds interesting. And finding a mutation back then was different than it is now. Now we can sequence a genome in a week, that's fine. But they had to really do it step by step, piece by piece, very meticulously, a lot of work. And at some point they figured out that it had to be, the mutation had to be in this region of 500,000 base pairs on the X chromosome. And they knew that the region had about 20 genes. So then they just sequenced each gene one by one. And of course, the last one they tested is where they found the mutation. So you can see it here. You can forget about it if you want. But there were 2 adenines added in exon 8 of this gene. And that introduced a premature stop codon, which made a premature terminated protein and made the protein non-functional. The gene wasn't described previously, so they just named it based on its characteristics. It looked like some other genes, so they called it FOXP3. What they did in the same paper, they showed that this FOXP3 was actually the cause of the disease. So if they gave those mice normal FOXP3, then the mice were fine. And then this is, I also think this is amazing. They had 3 papers back to back in Nature Genetics. So one of them was with the mice, and 2 of them were on a human disease, X-linked neonatal diabetes mellitus enteropathy and endocrinopathy, IPEX syndrome, which only happens in boys who usually die of it, or back then at least, they die of it at a young age because of widespread autoimmunity. And they found that actually in that disease, you also find mutations in the FOXP3 gene. So they both solved a mouse disease and a human disease all in one go. And this is what got them the Nobel Prize. It sounds a little bit like I've now told you 2 different stories. We've got the CD25 positive T helper cells, which can rescue autoimmunity. But we've also got unmutated FOXP3s, like normal FOXP3 that can rescue autoimmunity. And there was Sakaguchi again, who thought those 2 must be linked. And indeed, 2 years after the FOXP3 identification, he showed that FOXP3 was indeed the gene that is specifically expressed by those CD25 positive T helper cells, and that if you put FOXP3 in T helper cells, that they become suppressive. So the work from these 3 people have described something that we now consider textbook knowledge, that FOXP3 positive, CD25 positive T helper cells are the ones that suppress the immune response locally in the tissue, that they are the ones that drive this peripheral immune tolerance. That's quite a good story, but why do we care? Well, right? I spoke a lot about not wanting the immune system to respond to self. So it makes sense that this is an issue in autoimmunity. So autoimmune diseases like rheumatoid arthritis, systemic lupus, type 1 diabetes, they're all mediated because your immune system starts reacting to yourself. And in a lot of those diseases, you have an imbalance in the immune system. You've got too much pro-inflammatory T cells and not enough of these regulatory T cells, of these Tregs. So we're starting to, we've now learned a lot more about those regulatory T cells than what I just told you. So now we're at the point where we start thinking about, can we use this therapeutically? I don't have enough time to list all of the cool things, but I do have one idea that I think is really nice. So I told you that those regulatory T cell, or the T cells, they are specific, right? They have a specific T cell receptor. What if we can have a regulatory T cell with a specific Treg, T cell receptor? Then we can suppress the immune response very specifically to an antigen that's causing autoimmunity. And an example of that is lupus nephritis, where there's a very severe kidney inflammation, and it leads to destruction of kidney. People often need transplants. And one of the hallmarks of this lupus nephritis is they've got anti-Smith antibodies. So what this group did is they engineered T cells, Tregs, with a T cell receptor that's specific to this Smith antigen. Then, to prove that this worked, they did a lot of in vitro studies, but they also gave them to a mouse model, a humanized mouse model of lupus nephritis, to see if that could help rescue the disease. So they looked at proteinuria, which is the presence of protein in the urine, which you get if your kidneys are damaged, because they can't do the filtration properly. And you see that by week 8, if you don't add those any regulatory T cells, you get quite a lot of proteinuria in those mice. If you add just a bunch of regulatory T cells without specificity, we call them the polyclonal Tregs, then you don't see an effect on the proteinuria. But if you add those Smith-specific Tregs, then you get a reduction of your proteinuria. So this would be something in a disease where we know the antigen. We can go in with regulatory T cells and very specifically suppress only that response. Because if you would do a blanket, let's just upregulate the regulatory T cells, I mean, we also still want our functional immunity, usually. So this is a way to make it very specific. And this is now, they're trying to see if this can go into clinical trials. So that's autoimmunity, but a thing that maybe people don't think about a lot when talking about immune tolerance is actually that it's also important in cancer. So in cancer, tumors are actually very good at evading the immune system. They have a very good system where they actually induce regulatory T cells in their environment, so that your own immune system is like, nothing going on there, I don't have to attack it. Well, you kind of do. So in cancer, there's actually, the balance is the other way around. You've got too much regulatory T cells. So there's a lot of strategies by which they are trying to address this, and again, highlighting just one. So this is the situation if you don't have any treatment, you've got a cancer that's growing, you've got a cytotoxic T cell, CD8 is cytotoxic, but it's not doing anything because there's a Treg there that suppresses it and it says, no. What they've done in this paper, they designed an antibody, this green one, which binds to this receptor CCR8, if you can forget about the specifics, but it binds to this receptor. And because it's an antibody, it will recruit other killing cells of the immune system, which will then start killing that regulatory T cell. And because that regulatory T cell is killed, then the cytotoxic T cells can start doing their jobs and kill the cancer. So that's one of the ways, or those are two of the ways in which regulatory T cells are now being used to actually try to treat human disease. Of course, there's still a lot of things to be done, and I think the most prominent one, actually, the one that I'm currently running into a lot in my research, is there are no really good markers for human Tregs. So I said FOXP3, CD25, great, we've got markers. Well, actually, that mostly works in mice. So these markers are also present in human, but they're not that specific. So that's something that still needs to be done. We're also starting to understand that there are different types of Tregs. Some of them are FOXP3 negative. And the things that we still need to do is improve production efficiency for clinical use Tregs, of course, do those large trials. And things that we're also starting to look into is a situation where you also need tolerance, but it's not naturally there. So with transplantation, you actually don't want an immune response against a transplant, preferably. So is there something we can do to specifically get that tolerance against the transplant? And in pregnancy, it's also important because the baby is partially not you, but so your immune system needs to learn how to tolerate that. And if that tolerance goes wrong, you can get complications. So if we can find ways to boost that tolerance, that would also be very valuable. All right, sorry if I went a bit over time, but I hope this was clear, and happy to answer any questions.
Thank you very much. It's nice to hear that first started with happy feet and then some very unhappy mice and then eventually an hopeful ending. I'm sure there's questions. Please raise your hand.
Yes, thank you for your very nice and interesting talk. I was wondering, because in the slides about cancer, you mentioned that there's a reacting cell that tackles the cell on the left.
Yeah.
I forgot the names.
This one. Yeah.
But isn't that Treg from the cancer cell like a sort of mimic of what the rest of the body has as Treg, so that if you inject that effector cell, it would attack other Tregs in the entire body as well?
Yeah, so that's a good question. So actually this receptor, CCR8, is a chemokine receptor, and chemokine receptors are used by cells to migrate to the site where they need to be. And CCR8 is very specific for cells to migrate towards a tumor. So in the rest of your body, most Tregs don't have CCR8, only in that tumor microenvironment.
Okay, cool.
Yep, good question.
About T cells, I always have to think about HIV. Does this also come into this story, or is this a completely different?
Yeah, no. So what HIV does, it infects T cells and starts killing them.
So it disrupts this whole process.
Yes, so it just kills the T helper cells.
Okay.
And if you remember my picture from the first slide, like the T helper cells are kind of central in the whole immune response.
Yeah.
So HIV just kills all of them. And then your immune response crumbles, and that's why when you've got AIDS, you die of infection.
Yeah, got it. Okay. Maybe final question here.
Yeah, thank you for this talk. I was just wondering, so here you show tumor killing, and I was just wondering how generic can this be? Can it be used to sort of upregulate or boost the immune system against any type of tumor, or is this specific?
I think this approach would be specific because it's targeting those regulatory T cells and usually solid tumors then. So like leukemias are more difficult because they don't have that typical microenvironment. But if you've got solid tumors, then they usually have some cytotoxic T cells which are there but not very active. And you usually have the regulatory T cells in there that can be targeted like this. Yep.
Okay, with that, I would like to thank Wendy once more. Give her a big round of applause. I think we learned a great deal about how complex the immune system is and how small steps are important to understand. But now we have to move on to the next prize, which is the Nobel Prize in Chemistry. Monique van der Veen from University of Delft, Technical University of Delft, will explain all of it. Monique is actually from alma mater is Leuven in Belgium, where she also did her PhD, and actually works with the kind of metal organic frameworks for various applications, and therefore it's really an honor to have you here and explain all about the Nobel Prize in Chemistry. Monique, please, the floor is yours.
Thank you, Gert-Jan. I'm very happy to be here. I also realized I'm so in awe with the Nobel Prize going to the development of the materials that we work with in the lab every day that I completely forgot to put my own name somewhere on the slides. But so thank you for the introduction, Gert-Jan. So these are the three men that won the Nobel Prize for Chemistry this year. And I'm going to show you a bit of a timeline because it's not just a class of materials, it's become actually a whole field of research within chemistry or material science, as you will. And my own timeline started here in 2006 with my master thesis at Leuven. Who's working now on their master thesis? Yay. So maybe in 20 years' time you will say, hey, remember my master thesis? Anyhow. But what is it about? So the name, yes. So this is a metal organic framework. So what you see is, you actually see a lot of empty space, right? And this is on a molecular scale. I guess I can presume that people know what molecules are, right? So you have tiny spaces around the size of a molecule, very crystalline, regular pores. And you build up the material on the one hand from what you see here in the middle of the blue tetrahedron is a zinc ion sitting. Just remember salt ions. Some cluster there. And these clusters are linked in a very, geometric way via organic linkers. So you have like nodes and struts, right? And you get to a structure. So that are metal organic frameworks. And I want to first show you what came before them You know, what was the adjacent fields, what were they about before they were discovered? So we had zeolites. We still have them, by the way. I think almost all your synthetic clothes or whatever material you have all those molecules and materials around you that are synthetic have likely seen a zeolite in their journey towards you. But who knows what a zeolite is? Okay, a few people. Anyhow, it's a material that also has these tiny pores, right, on the size of molecules. But it's purely, it's actually sort of glass with tiny holes. I think that's the best description. And it can actually function as a molecular sieve. So that means, you know, some molecules will be too big and can't pass through. So like a molecular sieve, right? So you got some molecules can pass through, others not. So it's very effective at separating molecules. You can also imagine with this image that maybe a very big molecules goes through and then the material has like sides that make it, you know, that can cut it up into smaller molecules as a catalyst, right? It also does that. And in that capacity, it's been hugely successful in the 20th century and it's led to large-scale industrial application, and it still is today. So that's zeolites. So they were there. So that's the porous space, as you like. But on the other hand, there was also a very other prolific field out of, and it's still around as well, metallo-organic chemistry, where you have like ions in the middle, right? Like if you think of salts are ions, right? So ions in the middle, and some organic ligands around, right? It's also a prolific field. They had the Nobel Prize already more than 100 years ago. There's also applications for them in industry, not as large scale and huge as in zeolites, but there is. And what is great about them is that you can think of sort of any complex almost, right? You can use the whole periodic table, you can think of whatever ligand around it, so there's this huge versatility, which compared with zeolites is just glass with tiny holes. You don't have a lot of space to change the material, right? It's great at what it does, but you have limitations. And then you think, oh, but then I should just stick with the metal-organic complexes. Well, that's not true either, because when you use them, you would put them in a solvent, so they're in solution. So if you want to use them to make other molecules, and you have a separation problem in the end, because you need to have your complex that is very expensive complex. You know, you need to separate it from what you made, so it's not handy. Hence the not as large scale production. So that is why people got excited when and also in the 90s, they were trying to marry sort of these two fields. They were trying to find ways to have these complexes like bound to surfaces, like glassy surfaces, for example, right? So that was the status of the field then. And what happened then is that somebody figured out a way to create these complexes, like these beautiful with the ions and organic ligands, in a regular way, such that you got this repeating framework with holes in it, right? With space. And yeah, this is a publication of 1997, and I checked the whole issue in Angewandte. Everything was black and white then. You had to pay to get anything published in color, and nobody did that. So that is why it looks like that. And what this graph on the left hand is showing is that you have pressure here, and there are some gas molecules. And what you can see here is that these molecules, sorry for not providing the unit, that's really not a good practice. I think you're all learning that, right? Anyhow, but it's a lot that is going in. And what that proved is that this material, that it had permanent porosity. And that was key. So this was the first time that somebody could show, hey, but these materials could be like zeolites, but then with a lot of versatility that zeolites do not have. And so that was by Susumu Kitagawa, so one of the 3 winners. And as you can see here, you have the ions, and they're sort of linked in 2D by the linker. So you have like this regularity in 2D, and then it's like stacked on top of each other. And then 2 years later came the next paper. This was in Nature, so that was in color by default. But I did check the whole issue of Nature. Compared to all the other papers published in that issue, this was a very fancy picture. This is a fancy picture for the time. And again, you can see that and here you have a unit, that it can absorb a lot of gas, right? If you look at the unit, you can see like it can take up 80% of its weight in nitrogen, so that's a lot. Like there's, and this yellow circle is conveying like, wants to convey like there's all this space inside. So it's about emptiness actually. That was in '99, it was by Omar Yaghi, one of the other 2 winners. And what was extra special about this one was that you have this regular connectivity, not in 2 dimensions, but in 3 dimensions. And so it also showed permanent porosity. So now we can add this to our timeline. First MOFs with permanent porosity. And oh, I wanted to say something else about this paper, because this was also the first paper that gave it a name. So this is where the name came from, Metal Organic Framework. So that was coined by Omar. So first MOFs with permanent porosity. So what's next? I think one of the key ideas is that the concept of reticular chemistry, it sounds complex, the word, but what it wants to convey is that if you have a structure like this, right, you can sort of think of these clusters here as these balls and these linkers as these struts, right, and you see how you get like, you can build a 3D structure like. And then here you have a little bit more detail that shows very specifically like the connectivity of these clusters, right? But what if you could pre-design those clusters, right? So that you know beforehand what kind of connectivity you're going to have in both parts, the linkers and the nodes. Then you can design a lot of different topologies and not only get a lot of versatility, but you can engineer it, right? At least that's the idea, and it works up to some extent. Of course, when you try to make something a reality, it doesn't always work as you planned for, but it does. But it does also work, and that got people really excited, because then you can really, start dreaming about any property you would like, right? And people have been making all kinds of beautiful materials using almost anything on the periodic table of the elements. Also here in those elements of which many of you will, I don't think I know actually, I remember the name for each of the abbreviations here, but yeah, so that's the versatility, reticular chemistry or design. And a lot of people started entering this field because in essence, well, is anybody of you an organic chemist who has made an organic molecule? No? Okay. Good for you. No, because the process, if your job is to make a new organic molecule, it's probably going to be like a 15-step synthesis, and you start with 10 grams, and your reaction isn't complete, so you need to also purify and separate, and it's very tedious work, and then maybe you end up in step 14, and you only have a few milligrams left, and it's too little to do step 15, and you need to start over. Right? Well, if you want to make a MOF, what you do is you put your metal salt and your linker in a solvent, and you put it in the oven, like muffins, and they're porous too. So it was an easy field to enter as well, and a lot of people started doing that, including my thesis supervisor. And this was my daily supervisor in my thesis. So he was in a zeolite team in Leuven. And he was the first PhD student who was going to work with MOFs. So this was 2005, so it's really early days. And his first year of his PhD, he spent on this MOF that you've shown me, and it was a tragedy. I was very happy that I was a student in his second year of his PhD, because what happened is he synthesized the material, and as soon as he separated it from the solvent, it did collapse. It wasn't stable. So there was an issue, and that's been fleshed out completely in literature now. And what is the case is that up till 30% relative humidity, it's fine, but if you go above that, it starts to deteriorate, in fact. And it starts at the outside quite fast, and then it blocks anything from entering. And it wasn't a problem for Omar Yaghi, who was making it, because he was in Arizona State University, which is in the desert. But it was a problem in Belgium, and you're close by in the Netherlands, so you understand why it was a problem. So, but luckily, I didn't have to work with MOF 5. He had abandoned that. But there was somebody else who, and the first one, who made the MIL series, which are a series of metal organic frameworks that started in 2002, the first one. And I'm mentioning here specifically because he passed away 8 years ago, but for many people in the field, he would be somebody who potentially could have been part of the list of Nobel Prize winners, but you can't get it posthum. So we will never know if that was the case. But of course, if a new research field is trying to establish itself, but is a huge problem with stability, then you have an issue. But what he came up with was very stable frameworks, essentially. And you can see, some examples here. This one even, you can throw in aqueous water with a pH of 1 and it's fine. For the chemists under you, that's extreme conditions, right? So it worked. And he made a whole lot of them. And what was special about it is that everybody before, and all the other people, they were focused on using +1 and +2 ions. Like you can think sodium, calcium. Well, they used other elements more, but these are the ones that are more commonly known. So anyhow, he went with trivalent and tetravalent ions, aluminum, chromium, vanadium, titanium, and so forth, and combined those with very acidic linkers. And it's much more tricky to make it crystallize, to get the material, but it's also much more stable. And this is actually related. This is often the case. Anyway, I will not go into those details today. So lucky me, I got to work with the mills during my master thesis. And maybe, and this is a question I often get from people, is like, but what does mill mean, or any of these names of MOFs? They're simply abbreviations of the institutes of where they were first synthesized. Yeah. And usually it's chronological, like 1, 2, 3, 4, and so forth. Ferret made other materials before he started with MOFs. That's why it starts here at 53. But it's really chronological. But some people also think it's fun. Hey, 1,000 is a cool number. I'm just going to name my whatever many MOF just 1,000. So it's anyway. People do their thing with names and MOFs. They don't really convey you anything about the structure of the MOF. That's on the naming, that's on the mills. So I think the mill is a very, the mill series, the start of it, is a very important point in the timeline of MOFs. This was what my master thesis was about, because up until, and still at that time in the 2000s, the field was a lot about finding new materials and showing they had, even bigger porosity, even bigger pores and so forth. But it was also when people started to look at well, what can we do with them? Explore a lot of applications. So it was a time of firsts, and the work that I got to do with Luc was one of those firsts, because we could show that a first time we could separate molecules in the liquid phase from each other using a MOF. And it's still being really well cited for that reason today. So applications became the focus, new concepts came. So Susumu Kitagawa, one of the winners again, he also realized pretty soon that, hey, but you can think about this framework as a very static thing, but you can also use it as a stimuli responsive material, as for example here with the guests going in and out, that maybe the structure changes completely. And he put down a lot of concepts of ways that the material could change in response to a stimuli, and quite soon also made a lot of them a reality, showed that you could not just have like a static glassy material with tiny holes, but then also this material that could sort of respond in a quite dynamic way, even though they are crystals. And then also the field was starting, so actually 2008 was the very first time there was an international MOF conference. And since then, people have explored it for a lot of applications and properties, and you don't need to read it all, but you know, because you can choose your building blocks, so you can think about what can I use to get a certain property, right? And I don't want to highlight them here all because I think you're going to go crazy. So I will just focus on a few. This one I particularly like. It's also something we work on. And that's water harvesting from desert air. So here is the desert again with Omar Yaghi. Because Omar, so this is actually one of his students from his team that built this device, and they harvested water from the air. And I think that there's also some movies going around where they actually drink the water, and well, yeah. But what was particular is that Omar realized if a material has a water adsorption isotherm with this shape, and I'll explain it to you what that is, it can get water from the air in the desert, which sounds really counterintuitive. So what you see here is that this is the amount of water uptake, and this is the vapor pressure. And if you're at 1 on this scale, it would start raining. So that's a bit the scale you have. And you're often around this range in the desert. And if you would have this very step-sized sudden uptake of water, you can play with that, because it will shift very slightly with temperature. So you can think, okay, we're in the night, you know, it's maybe 10 degrees. This is our humidity, and the material is full with water. And then the sun comes up, and then we're actually on this graph, right? But still, for example, this humidity, and it all comes out of the MOF, and if you can collect that, you have water, right? So it's a very neat idea, and I think because Omar, well, he grew up being a Palestinian refugee in Yemen in the desert. I guess this rung close to home for him. So that's a great application. But if you're noticing is that I keep putting achievements by Susumu and Omar on these slides, but there is a third winner, right? So what about him? Well, to be honest, I didn't know about him but what happened really was that it was truly that you progress in science by standing on the shoulders of giants. And in the International MOF Conference in 2018 in New Zealand, because some people did know the work of Richard Robson in the field, but many more did not. But he was invited to give a plenary talk in New Zealand. And here's a picture of him giving that talk. What came very clear to that in that talk to me was this is a very humble man, but he actually was the predecessor to the whole field that somehow had gotten forgotten. So let's go back to a publication of him in 89. So this is almost a decade before the earliest publication I showed you. And he made this structure, yeah, and again, everything was in black and white then. And maybe, so he published recently like a review article making more up-to-date images of the same structure. So you can see here in purple, there is a ion there, metal ion, or a salt ion, and then you have your organic linker here. And you can indeed see the same abstraction here, like abstracting things into the points of nodes and struts, right? He already had planned to make this structure by using ions that he knew would have this connectivity and linkers that had a certain geometry, right? So the whole idea was there. So that the pre-organized building blocks leading to this designed 3D porous. Well, at that time, the name MOF wasn't there yet, so it was a coordination polymer. In that same paper, you can find a whole lot of predictions about the field, what you can do with these materials, how you could potentially modify them, and so forth. They all came true. Everything is in this paper. And yeah, I think that says it all. They also met, by the way, Omar and Richard for the first time on this conference. I understand it was also the only time up until now, but I suspect they will meet soon in Stockholm again. So this is Richard Robson, and he had been working, he had conceived these ideas already in the 70s and 80s and had been working hard in making that in reality with, in fact, a very small research group. And, oh, yes, I do have one more topic, and that's COF20, because that's my favorite MOF now. Unfortunately, I wasn't the one to invent it, but that was George Shimizu and Roger Ma in Calgary University in Canada. So CALV is an abbreviation of Calgary Framework Materials. And this material here, you see what it looks like. I can name all the elements and the molecules, but I'll leave that for today. But what you see in this is a very sort of counterintuitive results on this graph, and I'll walk you through it. So what you have here in green is again a water absorption isotherm. I showed you that before, so you see that as humidity is going up, water absorption is going up. Right? And here we have the loading of CO2. That this is at a fixed concentration. So this is how much CO2 is being absorbed in terms of humidity. So you see that as if you go close to where it starts raining, that it's no longer absorbing CO2 because there's water. It's precisely what you expect, and that is also the big problem with finding good materials to capture CO2 from the air. Is that there is a whole lot more water in the air than CO2. This is not at 400 ppm like CO2 in the air, by the way. This is at 0.3 bars of CO2, I believe. That this is for using in, for example, fossil fuel plants where you want to capture the CO2 immediately after converting fossil fuel into the energy into electricity. Anyway. So it's going down, this is what you expect, but what is unexpectedly, because you have this green graph, and this is the water absorption when there's just water, but the blue graph is the water absorption when there is CO2. And suddenly you see that in the presence of CO2, this green graph shifts to the right. It's become more hydrophobic in the presence of CO2. That's very odd, actually. And that's quite unique about this material, COF20 specifically, that it can do that. So there was actually, they found this window where it can operate in absorbing CO2 under humid conditions, which is very attractive from an application point of view. In fact, it's so attractive that now there is a Canadian carbon capture, sorry, I forgot the word carbon here. But anyway, that they are selling CO2 capture systems at large scale based on this MOF. And BASF is doing the scaled up, ton scale production of this MOF, which is absolutely fantastic. And but why CAF 20? The thing is that if you just look at how much CO2 it absorbs, it's actually just a mediocre MOF. Or even in the whole realm of materials that can absorb CO2, if that would just be your metric, how much CO2 will it absorb? It's, okay. But the thing is that it actually, all the ingredients, the linkers, you can imagine that some of these organic molecules that I've showed you so far are difficult to make, right? Remember the 15-step thing I just explained, right? That's costly, but this one happens to have extremely cheap organic linkers. One of them is even just oxalate, right? The ion in between is zinc. Zinc is also a cheap metal, right? So you have a cheap material. The synthesis is also under mild conditions. It's easy to upscale. It's a stable material. And like I just explained to you, it can absorb CO2 from humid streams. And so I think many of you are probably going to become engineer or are engineers, right? So I think this is a sort of a beautiful example of how to think about materials and target the right key performance indicators and not just go for records and one easy to measure metric, right? So this is a success story that I really wanted to have on this slide, and I suspect that the Nobel Prize maybe also came now because it's not only a very beautiful chemistry field, but it's leading to, real-world, large-scale impact at the moment. And I believe that, much more is to come also. And that's it.
Thank you very much. It's nice to see indeed that this is also a story of that good ideas or great ideas that lead to Nobel Prize never come alone, and there's always previous ideas, and there's many of those stories can be told. But I'm sure there's a few questions. Please.
I saw that you have, for example, water molecules adsorbed at the CAF 20. And how do you get them off? Should I think of a process like PSA, or do you just heat it up again and then it will vanish and your organometallic compound will remain stable?
This one remains stable. So it is indeed a TSA process that they have developed. Because also you need to think about, you don't only need to get the water off, right? But you also need to get the CO2 off with some kind of carrier gas, which cannot be nitrogen. So it has to be steam or concentrated CO2, which also only makes sense at elevated temperatures. So I believe this probably answers your question, right? Yeah.
Very small question and last question. Is the TUD one already in the making, or has it been made?
Well, people before me, because I'm not the only person at the TU Delft that has worked with MOFs. There are several TUD materials already, but also my group, we're not in the game of making new MOFs actually, because people are creating this wealth. We do put different functionalities on the organic linkers. We play around with it, but it's too subtle to name it. But we really like to understand how these materials work, and from there find out within the realm of what other people have discovered what can be used for all kinds of applications. Yeah.
Okay. With that, thank you, Monique, for a very beautiful story about beautiful materials. So the next and final prize that's going to be illustrated is by Hans Hilgenkamp, the prize in physics, who is a professor here at the university, also Mesa Plus director. And Hans actually did his PhD here in Twente, and afterwards he spent some time in Augsburg and also Zurich. And Hans has met one of the Nobel Prize winners, as he's going to explain in a little bit after setting up. So if you're ready, Hans, please go ahead.
Yeah, good evening. Okay. First of all, I have to apologize to the other speakers that I had another meeting, so I just bumped in during the previous talk, and I really enjoyed the part that I saw. In this last talk of this evening, I would like to introduce the Nobel Prize in Physics of this year. And the Nobel Prize in Physics is awarded to John Clark, Michel Devereux, and John Martinez for the discovery of macroscopic quantum mechanical tunneling and energy quantization in an electric circuit. So I'll try to introduce what that means in the next 20-25 minutes or so. So these are the people, as they look now, John, Michel, and John Martinez. And after introducing the topic, I will also introduce themselves a little bit in more detail. It's interesting to see the press release that came out after the Nobel Prize was awarded, and let's just go through it. It gives you a bit of a feeling for what it's about. Their experiments on a chip revealed quantum physics in action. A major question in physics is the maximum size of a system that can demonstrate quantum mechanical effects. This year's Nobel Prize laureates conducted experiments with an electric circuit in which they demonstrated both quantum mechanical tunneling and quantized energy levels in a system big enough to be held in your hand. So it's the size of the system that makes the difference here. Quantum mechanics is known already for a long time, and some of these effects like tunneling and energy quantization, as I will introduce in a minute, they were also known for a long time, but the specialty here is the size of the system that shows this quantum mechanical effect. So what is it about? Quantum mechanics allows a particle to move straight through a barrier using a process called tunneling. As soon as large numbers of particles are involved, quantum mechanical effects usually become insignificant. The laureates' experiments demonstrated that quantum mechanical properties can be made concrete on a microscopic scale. So this has already some funny aspects into it. A particle to move straight through a barrier. Well, how is that possible? We all know what happens if you throw a ball to a wall. It bounces back. The ball does not go through the wall. That's the classical picture, that there is a barrier and your particle cannot go through the barrier. So there seems to be something special in quantum physics, quantum mechanics, that it's possible for some particle to go through the barrier. And this is already very strange, but we know this exists. And actually, to understand this, people are using a picture not of a particle as a kind of a ping pong ball, but as a wave. This is in quantum physics, this is the famous particle-wave duality. So to understand these effects, people actually consider particles as if they are waves. And apparently these waves have a certain possibility, certain chance to go through such a barrier, if the barrier is thin enough and if it's not, let's say in terms of energy, not too high. So not always does this particle or this wave go through the barrier, but there's a certain chance that it goes through. And that's a process called tunneling. Now this is not to, as a starting point of a whole series of equations, but just to give you a bit of a background. So the description of particles as waves was invented basically in the 1920s. And there's a famous equation, the Schrödinger equation by Erwin Schrödinger, giving a mathematical expression for these wave properties of such particles. There are different forms. You can also have time dependence into it, but this is a rather simple form. And a famous consequence of this kind of wave picture of particles is the so-called particle in a box picture. So now imagine you have a box with infinitely high walls, and they're also the walls are also infinitely stretching out, so it's a confined space, and there's a particle in this space, and the particle has properties of a wave. Now, there are only very discrete situations how this particle can fit in this box. So let's say it's a half wavelength, or it's 1 wavelength, or it's 1.5 wavelength. Then at the edges, at the sides, this wave goes to 0, and then you have these nice wave-like shapes, just like you have strings in a guitar, also fitting in a certain length. That's the consequence of this Schrödinger equation, and considering that the particle is a wave that somehow has to fit in this space. Now, this may sound quite esoteric and strange, but it's basically the most fundamental principle underlying almost everything in physics. The fact that there exist colors, for example, that materials are conducting or insulating or optically transparent and hard and soft and chemical bonds, and all these things are all based on this notion, this physics, that there are these discrete energy levels, for example, of an electron in an atom. So it's quite profound thing. Actually, people were wondering at that time, okay, how to interpret actually this wave function, and what does it really mean that you should consider particles as a wave. And also at that time, there was a guy, Max Born, who said, well, the wave function describes basically the probability of measuring a particle at a certain position. So it's not that the electron is like a wave moving around, but it describes a chance, a possibility, that if you do a measurement, for example, you do a measurement of this, let's say, lowest energy state, where it says n is 0, you do a measurement exactly at 0, you have a certain chance that you would measure the electron at that specific position, which is kind of given by this wave function, or actually the square of the wave function. So for the NS2 states, for example, you have a bigger chance that you measure the electrons at one of these sides than in the middle, because the square there is higher. So quantum mechanics is all about chance, about possibility, about probability, and that's the key word in quantum physics. So it's a very important thing by Max Born, but Max Born is also has another quite interesting aspect to it. He's actually the grandfather of Olivia Newton-John. It is not so well known to everyone, but it's true. So at least people of my age, and well, there are quite a number of people in the audience who will have seen Grease, the movie. So Sandy in the movie, Olivia Newton-John, who's actually also tunneling somehow from a certain state to a different state during the movie. She's the granddaughter of Max Born. Okay, so this is then the quantum mechanical picture. So think about, wave-like properties, tunneling through a barrier and escaping in some way. So now the barrier is not infinitely high and infinitely long, but it's like a barrier also with, the possibility to go through. That's really quantum mechanics. And actually, this exists, and also in systems that we know. For example, the decay of uranium into thorium, uranium-238, releases an alpha particle. That's like a helium core. And then it turns into thorium, so it's a nuclear decay process. This is a tunneling process. There's a certain energy barrier, and the alpha particle has a certain chance to go through this barrier, and that's the decay process. And that's because of this probability, this chance. Nuclear decay is a statistical process, and the chance that it goes through determines in the end the lifetime of these radioactive materials. Also, nuclear fusion actually is a tunneling process, but I'll not go into that. Now, another very important aspect for the Nobel Prize is the concept of superconductivity, because the people did their experiments in superconductors. And superconductivity is a Dutch discovery. It was discovered in Leiden in 1911 by Heike Kamerlingh-Onnes and his colleagues. And superconductivity basically means if you cool the material down to sufficiently low temperatures, then the material lose their electrical resistance. Very strange property that normally you always have electrical resistance. Electrons moving through material create heat, and there's a certain resistance. But apparently in some materials, if you cool it down to sufficiently low temperatures, suddenly these electrical currents can flow without any resistance. There's a lot of applications also. So this was discovered in 1911. Kamerlingh Onnes got the Nobel Prize in 1913. Not specifically for superconductivity, but for making these very low temperatures where you can do these experiments. So we had to cool down helium to these very low temperatures and then do these experiments. And that was the key to the Nobel Prize. I see that the resolution is somewhat limited. Is that because of... No, okay, maybe the picture is just like that. Okay, yeah, superconductivity. For a long time it was not really understood why materials lose their resistance until the end of the 50s when Bardeen, Cooper and Schriever explained superconductivity in terms of Cooper pairs, and it's important for the rest of the story. Actually, Bardeen won 2 Nobel Prizes. Also, he was also one of the discoverers of the transistor. But for the superconductivity, these guys got the Nobel Prize in 1972. And to understand superconductivity, I have to introduce to you something very basic in physics. There are all kinds of particles in physics, and you can distinguish them in 2 types, fermions and bosons. So think about electrons, neutrons, protons, photons, Higgs bosons. You can all say, okay, either they are fermions or bosons. Forget about the complexity of the word. It's just 2 different things. And what distinguishes them is the spin. So an electron, for example, has a certain magnetic moment. We call that the spin. And there's a certain number attached to how strong this spin is. And for an electron, for example, this is a spin 1/2. So all particles which have this characteristic spin 1/2, which can also be -1/2 when it's the opposite direction, they are so-called fermions. So that holds for protons, for neutrons, for electrons. Bosons are particles that have an integer spin, where the spin property is different. Either they don't have a spin at all, or they have spin 1, or you could even consider spin 2, etc. That would be a boson. Typical examples are photons. Photons have a spin 1, and it's related to the polarity of the photon of the light. The Higgs boson also is a boson. Now, to convey the difference between fermions and bosons, let me just use this little analogy and tell you that bosons are very social particles, and obviously then fermions are very antisocial, asocial particles. So what does it mean? If you have a couple of bosons, they would be very happy all to be in the same state. Let's say this is like an energy state. They like to be in the lowest energy state, and they don't mind being all together in the lowest energy state. They feel completely happy with this. The fermions, on the other hand, they really don't like this. So you can have a fermion in this state. Well, if the spin is in the opposite direction, it's still okay. You can be quite on the similar level. But the next one really doesn't want to be in that state, and et cetera, et cetera. So they will occupy different states, different energy levels. There's quite a big difference between these 2 types of particles. So electrons don't like to be in the same state, right? Now, what was so special about the idea of Bardeen, Cooper, and Schriever? They said that there are certain effects that can happen in a material. For example, an electron kind of excites motion of atoms, atom cores, which have a positive charge, so they kind of feel attracted by the electron. And due to this motion of the atom cores, there can be an attractive force to another electron. So via this motion of the atom cores, these 2 electrons, they effectively bind, they form pairs. So if we have pairs of electrons, well, you have 2 particles with a half integer spin. So the sum is either, 1/2 plus 1/2 is 1, or 1/2 minus 1/2 is 0. So pairs of electrons suddenly become bosons. So if you have a mechanism that turns these electrons, which normally repel each other, into pairs, then you have a completely different state, and all these electrons then are very happy to be all in the same state, and that's the superconducting state. So they become one big super electron, all together in the same state, and then such a strong big super electron, they can move through a material, and let's say resistance effects are not strong enough to bind this very strong collective state. And that's the underlying physics of superconductivity. So these pairs, we call them Cooper pairs. Okay, let's see what my next slide brings. So we know now the concept of tunneling and of superconductivity and of Cooper pairs. Now, people have measured tunneling of electrons. Famous theoretician, and he said, well, you know, if in a superconductor all these electrons together are in the same collective state, if they form this one super electron, they may have similar quantum properties on the microscopic scale, since they're with so many together, as the single particles have on the microscopic scale. So you may be able with these superconductors to see the quantum physics that you normally see for single electrons suddenly for this big condensate, because they are all in the same kind of collective state. So Clark, Devereux, and Martinez said, hey, let's try this out. Somewhere in the 80s, when they looked still a bit younger. And let's use Josephson junctions for this. They knew about Josephson junctions. They thought, hey, this is a good thing. I'll introduce Josephson junctions in a minute. And they would have said, well, now this talk is going to get a little bit more technical, but hang in there, and hang in there. I'll get you through it. So the Josephson junction, what is a Josephson junction? This is Brian Josephson, who actually did his work when he was a student, for which he got the Nobel Prize later on. And he described the properties of, let's say, two superconductors separated by a barrier, so a tunnel barrier, where you may be able to pass Cooper pairs through. And he used this concept of this wave function, as I described before. A particle, a state, is described by a wave function. This is the mathematical expression for a wave function. This first psi between these model bars, it just means the amplitude, so the strength of the superconducting state, the strength of the wave function. And the other term is more important, this phi, that is the phase of the wave function. If you cannot follow me, it just doesn't matter. What is important is to know that if you have a wave function, there's a certain phase that is connected to this. It's just a number, it's the phase of the wave function. Now these superconductors, on one hand, the psi1, the wave function of one superconductor, and the psi2 for the wave function on the other side. Now, Josephson found out that there are two important equations that describe the properties of such a system, such a Josephson junction. The first is that there is a relation between the superconducting current that goes through and the phase difference. This delta is the phase difference, it's the phase 1 minus the phase 2. So that's a certain number. And this I is I0, let's say that's a constant, times the sine of delta. So the maximum value that you can pass through is equal to I0, and that's when the sine of this delta equals 1. So it has a certain phase difference. And he also found out that if you have a voltage over the junction, there's a time dependence of the phase difference related to that. So as long as the phase difference is constant, it doesn't have a time dependence, then there's no voltage. d delta dt is 0. But there can still be a current, because you have this this supercurrent flowing through. So that's a current without a voltage, that's a superconducting current. It's a bit technical, as I said, but this is the basics of a Josephson junction. Actually, in practice, if you want to model a Josephson junction even more complicated, you would say, okay, well, this barrier, there may be some resistance, some electrical, just normal conducting resistance. It's not, may not be fully a tunnel barrier, so you have to model an R, a resistance into it, and there are also some capacitive effects. It's not so important now, but the consequence is mathematically that there is a very nice analogy to describe such a Josephson junction if you take a picture like this, which is called the tilted washboard potential. So if you have, so it means that, for example, in the top situation, when there's no current, no electrical current flowing through, you can picture a kind of a potential landscape of hills and valleys, and then this little ball that is inside represents delta, the phase difference. And if you now apply a current, you start to tilt this potential landscape. So first, you know, you tilt it a little bit, but this ball is still not moving. It's still stuck in a valley. So there's no change of the phase difference, no change of delta. So the d delta dt is still 0. And so there is a current, because with the current you tilt this potential landscape. But the ball is not moving, so there's no voltage. So that represents a state where you pass a supercurrent through. That's this I is smaller than I0, this light blue. But if you tilt the washboard potential more, if you apply more and more current, at some point, you know, this ball escapes and it starts to move. And that means that the delta, the phase difference, starts to become time dependent. So the delta, d delta dt is time dependent, and then you have a voltage. So this tilted washboard potential is a very nice analogy to understand that, you know, when you apply more and more current, at some point you start to see a voltage because this ball is starting to move through this potential landscape. Now, if you now think back a little bit in this quantum picture that I showed you before, with this ball and this barrier, and then this wave and the barrier, you can also think about this particle in this potential landscape, that represented this phase difference, not as a particle, but as a wave function. And then there are, again, these discrete levels in this potential landscape that represent certain states in which this Josephson junction can be in. So these are still all superconducting states, but they have different energy levels, like a quantum particle in a box picture. Now, very complex, so I'm pretty sure you have difficulties following this, because you need really time to digest what this all means, what this particle means, what this delta means. But it basically says that you can view now such a Josephson junction as a kind of big system, a macroscopic system. You have a superconductor and another superconductor, and they are somehow coupled to each other. And there's a certain description of such a Josephson junction that you can describe in quantum terms. And now the question is, if you have my pointer is not working, so if you're somewhere in one of these states, maybe I can do it via this. Does it work with? This works as well. And suppose you're in this lowest energy state or in this energy state, and you tilt this washboard potential. At some point, you expect then, let's say, this motion. But if you think in terms of tunneling, you could say, okay, is it possible to tunnel from this state through this barrier and escape in that way? And so now this tunneling process comes into view again, but this is a macroscopic system. It's a macroscopic system of Josephson junctions coupled to each other. So if this would be possible, that you have this transition from the superconducting state to the voltage state by this tunneling process, so already before this washboard potential is tilted so much that this particle would start to move, and then you have a form of macroscopic quantum tunneling, and that's quite special because you have then this tunneling on this big system. The other thing is that you have these different energy states. So can you actually go from this state to this state and to this state, and then show the tunneling from these different states? Now, that's exactly what was done in the experiments by Clark and Deborah and Martinez. And this has already been technical enough, so I don't want to spend time too much on explaining all the details of these experiments. What they did is that they could show, by doing many experiments where they changed the current, that actually they saw that the chance that there is this transition from the superconducting state to the voltage state is already high enough before you actually classically would expect this motion of this particle representing the phase difference, that there has to be this tunneling process through this barrier. And from this experiment here on this side, they could see that you have these different energy levels of these Josephson junctions in the superconducting state. And this is basically for which they got the Nobel Prize. So it's a discovery of quantum physics in this collective state of electrons forming together a superconducting state. Now you may wonder, and that was also in the previous talk, were they actually the first to do this? No, not really. This is 1985. I've just digged out a few pictures this morning from 1981, where they basically do the same thing. And they also say in the abstract, macroscopic quantum tunneling in a 1 micrometer niobium Josephson junction, 1981, showing an experiment which is very similar. Another one, also in 1981, so this is IBM, this is Bell Labs. You see this tilted washboard potential and some measurements, basically showing the same thing, this tunneling process. So it's not only this tunneling process, but it's especially also these different energy levels within this washboard potential that made the difference for the Nobel Prize committee. Otherwise, these other people should have gotten it. I don't know if they're all still alive, but the macroscopic quantum tunneling and the energy quantization in an electric circuit. And that's also in the citation of the Nobel Prize. These both things are combined in this Nobel Prize. Okay, well, how do you picture this then? So this is this collective state of these electrons. Normally, classically, to go to the other side, you would have to climb the whole ladder and go over it. That's overcoming an energy barrier. They could show that these electrons can actually tunnel through the barrier to go to the other side, and they can also occupy different energy levels, and you can excite them actually from one energy level to the other using microwave power. Okay, let me just say a little bit more about these people personally, and also how why this work was so impactful. John Clark, Michel Devereux, and John Martinez. So first, John Clark. He's British. He was born in Cambridge, so he was already born and raised in an academic environment. He's now 83 years old. He did his PhD on Cambridge, and then he went already directly to Berkeley, where he stayed until his retirement. So he spent all his life in Berkeley. His reaction to winning the Nobel Prize was, to put it mildly, it was the surprise of my life, he said. That this work was Nobel Prize worthy had not occurred to us in any way. So it was really surprising. Actually, it was also a surprise for me. I was preparing myself for a PhD examination in Groningen. I still had like 10 minutes, so I was sitting in the coffee bar and I looked at the announcement and I saw John Clark, and I know John Clark personally quite well. And I just fell from my chair. It was not really the first one I would have expected to win the Nobel Prize. Michel Devereux, he is French, born in France. He's now 72. So this work was all done in 85. So you have to just count 40 years away from it. So he was 32 at the time. He did his PhD in France, and then spent time as a postdoc in Berkeley, 2 years only. But these were the 2 years in which he worked on this experiment. Then he went back to Saclay in France, and in 2002 he went to Yale University in the US. And then, interestingly, he became the chief scientist at Google. Google is working on quantum computing, and he is the leading guy. I will come to that in a minute. And he's also connected with the University of California, Santa Barbara, and still also with in Yale. And his reaction was he just slept through it, and then he woke up at 7, and he looked at in his computer and he saw all kinds of emails, and so he thought it was a joke, and then he called his daughter who lived in France, and she said, "Well, no, it's really true." So then it became real to him. Okay. John Martinez, he's an American, born in 1958 in the US. He did his PhD at that time with John Clark in Berkeley. So it was the team. John Clark was the professor. Michel Devereux was a postdoc, and John Martinez was a PhD student in 1985. Then actually he went to Saclay, so he went to France, and NIST in Boulder, and he's now at the University of Santa Barbara, and he also was at Google. So in 2014, Google said, okay, we should go into this quantum computing, and they hired John Martinez as the boss, and he did a quite impressive job building up a quantum computer, but he was a bit too directive, I think, to lead a big team. So at some point didn't really work anymore at Google, so they stopped this collaboration. And he returned back to the University of Santa Barbara, where he's still a professor. His reaction was, actually he was at home and his wife was awake, so she was still reading a book when the news came out. But she didn't, she decided not to wake him up, so she called, she got a lot of calls and interest, so she answered that. And then, so at 5:30, he woke up, and then his wife told him, "Hey, John, you won the Nobel Prize." And then from 6 o'clock, all kinds of reporters came to their house and all that. So that's at least the story as they tell it. Okay, so why is this so impactful? You hear a lot about quantum computation, and there are different forms of quantum computers. Here in Twente, we actually got very good in making optical quantum computers. But the very big activity is superconducting quantum computers. And they use actually the same concept. So you see here on the left side, you see the basic circuit, and this box that says EJ is a Josephson junction. And in parallel, you have a capacitance. And we call this now a transmon qubit. That's the name for it. And you see this potential picture there, and you see these different states, 0 and 1 and 2. And the quantum computer works on basically using what we call superposition, so using the 0 state and the 1 state as the 2 states for the qubit, and doing all kinds of quantum operations. So it would take me another lecture to explain what quantum computation means, but they actually use this concept of this potential landscape with these different energy states that was first measured by these 3 people. And actually, Google has been betting on this very, very strongly, with Martinez and then with Devereux in the lead. And they make now chips with more than 100 of these transmon qubits all coupled together. And just last Thursday in Nature, they brought out a paper where they did a calculation on some kind of atomic structure that they did with this quantum computer, and they could show that it was like 13,000 times faster than what you could do with the fastest normal supercomputer. So this is something we call quantum supremacy. So that has been something that people have trying already for a long time, showing that you can do something with a quantum computer, something meaningful, a real calculation, much faster than what you could do with a normal computer, even if you have the best possible supercomputer. And so the claim was just made last Thursday that for the first time in history, this quantum supremacy has been reached in such a circuit, a transmon circuit, that relates very strongly to this original experiment for which they got the Nobel Prize. Now, is there a link to Twente, you may wonder? Well, for me personally, there is very strongly. I know John Clark very well. This is John Clark roundabout in the mid-90s, and this is the cover of my PhD thesis. They were working on the same things as we were here in Twente. This is a superconducting squid structure, which also includes Josephson junctions. At some point, we were the only 2 labs in the world that could do this, the lab of John Clark and here in Twente, making these things and showing that it worked. We had a lot of interaction at those days, so we were like competitors, but also good friends. He's an extremely friendly guy. Met him a lot at conferences, and also he was here in Twente several times, and we had a lot of contact also afterwards. But more important, there's another very strong link to Twente. That's via Benny ten Haken. Benny was a professor here who passed away this year. Benny was working on superconducting magnets, big scale superconductors, but he wanted to do something else. He wanted to have a little bit of a break, and he went to Berkeley. So I just quote from his oratie, from his inaugural lecture, which he did in 2019. And it's in Dutch, but basically it says, okay, I was looking for a new challenge. So in 2002, I went for 9 months to Berkeley. And there were all kinds of exciting developments in MRI, magnetic resonance imaging, at extremely low magnetic fields. In the group of John Clark, we demonstrated that even in the magnetic field, as you have it here in this room, you can do MRI. So MRI, magnetic resonance imaging, we also all know this from a hospital. You go into this big system, and that's a very big magnet. That's also the reason why Benny was interested in this, because he was working on big magnets. Then he went to John Clark, and he learned you can also do MRI in very strong, very small magnetic fields, if you have these squid sensors that I just showed you before, as the sensor for your MRI experiment. So he got into this field of low field MRI. And then in Berkeley, he got a phone call from Maria Peters, who we know as Riet Peters. So she was a professor here in Twente. And Riet Peters said, well, we're starting a new activity here at the university called technical medicine. Would that not be something nice for you? And Benny liked it very much, and he said, hey, that sounds like a very nice new initiative. So Benny became the first research professor for technical medicine, and he introduced this MRI, low-field MRI here in Twente. So technical medicine, of course, has developed very strongly, and it's still there. It was the basis for the TechMed Center here in Twente. We still do a lot of MRI within the TechMed Center. So the core, basically, of this is with Benny's sabbatical in the group of John Clark in Berkeley. Okay, that brings me to the end of my talk. Let me just flash the 3 people again, and the Nobel Prize and the quotation, and then thank you very much.
Thank you, Hans. A quite elaborate story, but maybe there's some questions from people that... Any? Yes, there.
You showed us some formula,
Yep.
and the formula was I is I0 times sinus delta.
Yeah.
But if you tilt your washboard, so to say, then I should be larger than I0. So what is happening with that formula?
Yeah, then so this formula holds for the superconducting current. And then this delta, so the d delta dt becomes non-zero, so then you get a voltage. And what's actually interesting is that while you have the voltage, this delta is changing as a function of time. So for example, if you keep the voltage at a certain fixed number, let's say 1 volt, then it means that d delta dt becomes linearly dependent on the time. So the delta is growing linearly in time. If you put that in the first equation, then you have I is I0 sine of delta, which is linearly changing with time, and it means it starts to oscillate. So it's quite special that the superconducting current starts to oscillate at a certain voltage over the Josephson junction. So that makes the physics of Josephson junction also quite special.
If you shout, then
yeah, that's an interesting question. So when quantum physics was kind of discovered in the 1920s, and this whole concept of probability came up, people started to think about, how to interpret this probability. There's a certain chance that something happens, but there's also a certain chance that something else happens. And one of the interpretation was that, here in this world, this thing happens, but there's somewhere else at the same time a world is created where the other thing happens. This is something you can very difficult. It's very difficult to prove. But I made the joke once on the radio, that actually maybe Trump has kind of, made the ultimate proof that there exist alternative worlds, so that he could also get the Nobel Prize for Physics, providing this ultimate proof for that. But these are all kind of esoteric interpretations of quantum physics I think if you just follow, it makes also the understanding of quantum physics quite complex and sometimes a bit magical, which I think is also not so ideal. So I always, when I introduce quantum physics, I always say, okay, the key is that it's all about probability and chances. That if you think in terms of chances, then you start to understand a lot of the quantum physics.
Maybe a very simple question, but you said that the size was important here, eh? That this is a macroscopic.
Yeah.
What is now the largest quantum object that you know of?
Showing these kind of things. It's basically this system, Josephson, as far as I know, these Josephson junctions switching to a different state in a quantum mechanical way.
This is micrometers or so, or millimeters, or what?
Millimeters, millimeters. Yeah.
Any final thoughts, questions? If not, then I would like to thank Hans once more for a nice story, but also our previous speakers, Monique and Wendy, and I would like to thank you for your attention, and I hope to see you next year again at the 26th Nobel Prize Lectures in Twente. Thank you for your attention.
Thanks, Gert-Jan, for moderating this session.